Hello. So today we will start to practice with k-nearest neighbor, and we're gonna adopt some dataset called cancer dataset. It's cancer.csv. So first of all, before we start, let's import some libraries that we normally utilize. So we always import the NumPy. We need it sometimes. Maybe we didn't talk much about it, but just in case if we need to create maybe an array or something. And then we need to import the pandas as bd, and then we need to import matplotlib dot python plot. This is very important library. We import it as plot, and we would like also to import Seaborn. So Seaborn, we're going to utilize it for developing the correlation matrix, and we can also use it for the confusion matrix in our classification case. Seaborn as SNS. Then we would like to upload some of the libraries in scikit-learn. So we're going to say from sklearn, what we need to upload here is sklearn.model selection. This is very important. We need it. Okay, and we can import it. Import the train as we did before. Train test and split, so we can split the data. And from sklearn, one more time, we this is for the first time. We're gonna do some sort of pre-processing for the data. Import. We're gonna import something called standard scalar. This is something we talked about in the lecture, and we're gonna apply it here. Now the next thing, we would like to import the algorithm that we're gonna adopt, which is k-nearest neighbor. So I'm gonna say sklearn dot neighbor, and we're gonna call it, gonna say import k, it's called n k neighbors classifier. Okay. For the evaluation of the result, we need to import some matrices. So I'm gonna say from sklearn, I want to import. By the way, I would like to tell you or show you how can we import data from sklearn, but at the same time we're gonna also download the data from GitHub. So if I would like to import data sets from sklearn, I have to import data set, and then I have to do model underscore selection, and then matrices. Then I would have to say from sklearn dot matrices. Okay, I need to import some evaluation criteria like accuracy underscore score. I can also create something called classification underscore report, and I can also import the confusion matrix, which is very essential when you have a classification problem. That's the first part. Let's execute this and see if everything is going fine. All right. All right. Now, next thing we would like to do is to load the data set, and I think we did before do a data set by defining a data frame, and we say panda bd dot read csv, our file here this time is read, I'm sorry, read underscore CSV, and then we read the file. The file this time is called cancer.csv. Let me show you how I did a search. Like if I go back like this and they say search for cancer.csv, here we go. I search for cancer.csv. The first found items here is called cancer.csv. Now this file is actually available on GitHub. So in order to download the file, I'm gonna say download zip file. I'm gonna download it here and then save it. And then I'm gonna go to my folder and then extract this one, extract all, yes. And then I have the folder here. I have another folder. I have the file now. Okay, I can say I can cut this file. Normally I keep the files CSV here, so I'm gonna put it here, Control V. This is cancer, and I'm gonna just delete all these files which is not required, and then I'm gonna go here to my folder on Colab, and then I'm gonna upload the file. I'm gonna say go to cancer, upload it here, okay, and then it's uploaded now, it's here. And then if I would like to execute this, I can execute this. And if I would like to do some sort of visualization, I can say df.head and see what is inside this file. So this file has a number of inputs. It has the first column is diagnosis, and it has radius, mean radius, radius mean, texture mean, perimeter mean, and so this is the size and the characteristics of the different attributes or features. Let me show you another way of uploading this data from the data set from that we imported, the data set from scikit-learn. I wrote a simple code here which can help doing that. Let me just copy it here and then we can explain what's happening. So we called the dataset cancer dataset, and then we said datasets dot load breast cancer. So we defined the type. We got this dataset you see from the dataset here from scikit-learn. So we imported from scikit-learn dot load, like when we said before, like load uh, um, bd read CSV. So but here we are loading the data from the scikit-learn, and then we create a data frame. So we say bd data frame data, and then we call it cancer underscore dataset, which is this one dot data. So this will be the dataset that we're gonna utilize for our experiments. And then we define the column names. So we say columns cancer dataset, which is the same name here, dot feature underscore names. And if I just run this, let's remove this part first and see if we execute this. If we execute this, you see the distribution of the data. Let's call it head for simplicity reason. We don't need everything, so we call it head. Now you see the first column actually is the mean, radius, blah blah blah. It's the features. And if we go till the end, you will not find here the target. So the target is going to be part of the data. So I need to define, say, df target equal cancer dataset dot target. That's what we should do. And in this case, if I do that, you will see that the last column now became the target. So if you prefer this way of uploading the data from scikit-learn, that's fine. If you prefer the old way of downloading the CSV file and just say bd load the bd.read underscore CSV, you can do that and define the data frame. Okay. For now, that's what we're gonna do. That now the next step is we need to decide it on the independent variables. You remember in regression, we defined the dependent variable is the y, and the independent, which is the label in this case, and the independent variable were the x's or the inputs. So in this case, I would like to simplify actually the problem. So I'm gonna do the features. I'm gonna call it, of course, feature for simplicity reason, and then say df, and then I'm gonna gather two features only from this data. The first feature is gonna be I would like to get the mean radius. I think if we go to the beginning, here we go. I'd like to get the mean radius as one of the input features, and comma the mean texture. Okay, and my label will be the target. My label will be in this case the target, which is going to be the f target in capital, like this. Let's execute this and see if everything. Oh, there is a problem here. Texture, yes, we have texture. It should be small. Okay, here we go. So we were able to upload that. Now this means that I have two inputs now: the mean radius and the mean texture. Okay, so these two columns will be the input features, and then my output will be the class, which is target in this case. Okay, now before we continue, what we need to do here is we need to do some sort of visualization. So I would like to see the relationship. I'm saying here we need to, of course, build a classifier that can detect based on the two inputs, the mean radius and the mean texture, if the class is benign or malignant or type of problem. So here I would like to show how the correlation between the detection of a cancer happens. So I'm gonna plot the scatter plot that shows the relationship between or how the data looks like, and then I will do the confusion correlation matrix. But first of all, let's visualize the data. So as we did before, what we can do is we can plot dot figure, and we will define figure. So to manage the size, and then we say fig size equals. I think 4 and 3 will be adequate for visualization on the screen. And then I'm going to say plot dot scatter, and then I'm going to define what? I'm going to show the relationship between the features, the mean radius, and the mean texture of the tumor. So I'm going to call this mean. I'm going to say features, okay, and then I'm going to use the mean. Let's make sure that, okay, here we go, so we don't make a mistake with the spelling. And then the second attribute is the features, and then we can utilize the mean texture. Great. And then after that, I'm gonna put a title, say plot title, and then say mean texture and radius colored by detection of cancer. Okay. Of course, if you would like to add a label, again, we did this before, plot x label, and we can call this mean radius, and then plot dot y label mean texture, and then after that we can do plot dot show to display. So now what I'm going to display here is going to be the relationship between x and y, and that's the data. But now because we do not we haven't used any like relationship or relate this to the label, we should add here the C and say label. So now we identify it based on the label. If I run this one, here we go. Okay, so that shows the relationship. So the yellow and the red or dark red and the label along with the label. So it shows how they are. If you would like, as we said before, you would like to change font size, you can say font size equal 9, for example, or 10, something like that. That's easy. So that shows when the relationship between the mean and radius, and what are the labels that we have for Cancer, if it is red or if it is yellow. So I'm not sure which one is the one and which one is the zeros. We can test it, but just in case, this shows two classes in the data set. And if you look at the target actually has only ones and zeros. So here is zeros. Okay, if I would like to show this is the head. If you remember, we can also show tail. Okay, like this. Let me just make this in another code so we do not mess up with data. Here we go. So it's the tail. We have also one here, as you can see. By the way, also you can do like head, and then possibly you can say n equal 5 or 6. I think this will allow you to get some values, like like number of records. If you would like to have like a specific number of records to be displayed, you can do that. See that? So that shows from 0 to 13. Just in case, I'm saying if you are interested to know about that. So now we were able to show the distribution of the data, and the next step is I would like to plot the correlation matrix. The correlation matrix in this case actually is going to be a way to present the relationship or the correlation. How strong is the relationship of the mean texture and mean radius with the class, which is in this case is the target. So so simply I'm gonna do the following. I will just reunion these items one more time. So let me just take this. I'm gonna call it something different so we do not get confused. I'm gonna call it like df1, and I'm gonna add to this the target. Okay, I'm gonna add to this the target. So normally you give the full data frame. Okay, so now I'm creating a new data frame called df1, and then I'm gonna calculate the correlation matrix. Simply I just have to say correlation matrix, and I just have to say equals df1 dot cor. Okay, so that's all. Once I do that, I can get the correlation matrix. So I'm gonna do the plot again. Let me just, to speed up the process, let me just take a plot like this and put it here, and then I'm gonna use the seaborn. I'm gonna say heat map. I will tell you why I'm defining something called heat map. I can directly say SNS seaborn dot heat map like this, and then provide the correlation matrix. Okay, like this. Okay, and that's it. Let's see what's the output here, and if I need to correct it or to enhance it. Say plot dot show. Okay, now here we go. So the heat map is not working correctly because of the type of the data. Yeah, I believe there is a mistake here. We should have this brackets. Here we go. That gives us out. Now, as you can see here, This gives the output without any numbers or data. As we explained in the lecture, we should have numbers here that can help us to know the data, the relationship. We just got like a color map. So the color map here on this column, it's, as we said before, it's 1 1 1, right? And then the rest will show the correlation. Now what I can do in order to enhance this, I need to add something called annotation. So I would say annotate, A-N-O-T, and then I say true, like this. And let's see what's going to happen to the plot here. Here we go. So that gives us the annotation. It gives us the numbers here on the column. And here this shows a positive relationship between the mean radius and mean texture. And this is the relationship between mean radius and the target. It's negative. So this shows the relationship. If you look at this down, uh, the triangle in the down here, you see that mean texture has with a mean radius has a relationship positive. It's not very strong, but the target has a negative relationship, but it's more strong. Here, the mean texture has a negative relationship with the target and so on. So this is what represents the relationship. I can still enhance the performance of this um, heat map. I can add, for example, CMap, as I guess we did something like this before. And in the lecture, we also talked about several format. If I say cool war, and that's one way. I like also to show something which is maybe we don't we might like to see it here. If you would like to see the decimal, the way that these numbers are displayed, I can use something called format, and then I can say format is uh, let's say 0.3f. So this is I'm gonna see like 3 decimal numbers. Okay, let's see what will be the output here in this case. Here we go. So we have 3 decimal numbers. So you can play with the format of these correlation matrix. Of course, I can add some title. Let me add some title here. Uh, add this title correlation matrix, and I'm going to change the font size to it, so it looks much better. There are also many ways that you can play with the title of this elements, the x-axis and the y-axis. That's why I call this heat map. So I can say heat map, and I can do that and say set underscore x tech. Here we go, x tech labels. You can play with this x tech label, and then say heat map dot get underscore x tech labels, and then brackets, and then you can say font size equal to, let me just correct this one, font size equal to, so you can play with, if I just select a very small font size so you can see the difference. Here we go. See, the font became very small. I can do the same thing for Y, and get the heat map for the Y. I can do the same thing. Let me just try to do it here. Let me make this 8 again, so that can help reduce the font size for the, I mean, like it's just some kind of better visualization. And for the CMap, you remember in the lecture we talked about several ways or several colors, if whatever you like, whatever you prefer. But I think this one is good because it gives us the blue color, which shows a more stronger relationship, and then a less color, lighter color with a less strong relationship. Now the next step is to split the data to training and testing. We have done this before. I would say x train and x test, comma, y small train, y small test, and then this will equal to train underscore test underscore split, and then we feed the features in this case and their label. Okay, all right, and of course we need to say what is the test size. So as we always do, we keep the test size as 0.2, and then we need to define the random state, and let's call it 42, for example. Okay, now if I execute this, now I was able to split the data to train and test. Now the next step is actually standardization of the data. As you can see here, the data, if you look at the data carefully, this data is like in the range of hundreds, this data in the range of thousands. That might be a problem for the model development. So standardization is very essential process in these cases. So simply how standardization work, I can call something called standardized scalar function, and this function will do two things. First of all, it will calculate the mean, which is the average, and the standard deviation for each feature. So it will calculate the mean of this first column and the standard deviation of this column. Then the mean of this column and standard deviation for this column. The next step, it will subtract the mean from every single element in this column and then divide by the standard deviation again each element. So how we call this, that's the way we're gonna do it. Let's go here and then write this code. It's going to be simply like this. I'm going to say I think it's better to yeah, I think it's better to get the equations straightforward. So to standardize the data, I'm going to call the function which is called scalar, and this will be as follows. I'm going to call scalar equal, and then I'm gonna get the function which I uploaded before, again the scalar standard scalar, this function, to create the scalar values. Okay, and then I would like to fit the scalar for the training and testing data. I'm gonna say fit the scalar to both training and testing data. Of course, I need to say to scale here the data. So I can rename the data, or I'm gonna overwrite it. I can say x train. I'm gonna overwrite it and say scalar dot fit, okay, underscore transform. Here we go, and then I'm gonna feed the x train. So this will overwrite the data. Um, Maybe in some cases we can change the definition and then move the values to the train and test, but I'm just doing this for simplicity reason. X test will equal to, I'm gonna say same thing, scalar fit, but this will be for test data, like this. All right, and then execute it. Now let's see the data set. So I know the first column and second column how it looks like. I can say xtrain dot head like this, and see yeah, this is not in a format uh, of frame. So here it is. So it's an array of values. As you can see, the values here will be most likely smaller than the original values. So here this is 2.9 something, this is minus 0.5 to the power minus 1, this is minus 3 to the power minus 1. So it's in array format now. If I look at the d type here, it's a float value, so it has a float value. All right, so it means now I have the data in the like scaled. Now the next step is I'm gonna use um, now initialize. I want to initialize the k nearest neighbor model, okay, and start to do the classification. All right. So the next thing I need to do is, as we did in the linear regression, I need to call the model and say k nearest neighbor. Remember the name of the k nearest neighbor, it's here. This is the k nearest neighbor classifier. Okay, now if we do as we do in least square estimation, I'm sorry, in linear regression, I'm just gonna put this like this and have the brackets like, but in our case, actually, you must define the value for k. You must define the value for k, okay, because the k nearest neighbor needs to define the value of k or for k. So I have to say n neighbors, okay, and in let's try a value. Maybe you can call it, maybe you can make it 4, right, or something like this. I mean, we can use 4 neighborhood. That might be okay. All right, and then after that, I would like to train the model. I can say model dot fit, exactly as we did in the case of linear regression, x train, and then comma y train, okay, and then let's see what's gonna happen. It works. Now the next step is I'm gonna get the y predict. I will say y predict equal model dot predict. Here we go, and I'm gonna feed x test. Of course, in the case of linear regression, we did this for train and for test. You can do it, of course, but I'm just for the sake of time, I'm trying to avoid that now. So we're just gonna create the output y in the case of training, and then you can do it on the case of training and testing, as we said last time. Okay, now I would like to assess the performance of this model. So I would like to use something called accuracy score. So how good or bad is the result? So I will use something called, I will define some variable called accuracy. Okay, and then I'm gonna call accuracy the function score. Here we go. And then I'm gonna feed the y test, okay, and the y predict, which is I just calculated here. See that? If I have y predicted train and y predict test, I can calculate the accuracy over training and testing cases. Okay, here we go. So we did run this. Maybe if I would like to see the output, I can say accuracy and see what will be the accuracy in this case. See that? So the accuracy is 0.912. So the accuracy is not bad in this case with a 4 neighborhood. Okay, that might be a good idea. Last time I mentioned a way on how can I format this. So if you would like to format it, maybe an easy way is to if I would like to format it in an easy way, I can say f, as we said before, and then I say accuracy uh, uh, equals, and then I can define accuracy here. I just need to use curly brackets and then accuracy and then 2 colon, and then I will say 0.4f. This is a format for 4 digits, or if you want it to be for 3 digits, that's fine, but we have to have the closing here. Here we go. Sometimes this simple thing present a challenge. Here we go. Okay, so this is the accuracy in the testing case. This is, I can say this is accuracy in the testing case. Of course, you can calculate the accuracy on the training case. All right. Now, I can also calculate something called the classification report. So the classification report simply is called classification underscore report. As you know, we called it here before, or we imported it here before, classification report and confusion metric. You just have to call both of them, by the way, easily. I'm gonna copy this, Control C. I'm gonna go down here, and let me do something for simplicity reason. I'm gonna just create the output right away using a print command. So let me take a copy from this, or, and then I will say print, and then I'm gonna say classification report, and then I will use the command classification report, and I'm gonna fed again y test, comma, y predict. So right away, I mean, and then for confusion matrix, I will say print, and again confusion matrix, comma, confusion matrix. Again, I need to fed y test and y predict, because this is y predict test. And let's see what will be the output in this case. Here we go. So this classification report actually produced a relationship. I think it might be a good idea if I added a line here to make it looks nicer. Here we go. So the classification report shows the precision, the recall, the F1, and the support. So this is some attributes or some values. I mean, I think in the lecture we already covered what is a precision, what is a recall when we talked about the confusion matrix. And here is the accuracy. Forget about the macro average and weighted average right now, but this is accuracy, it's 0.91. Again, we calculated the accuracy here, it's 0.91. And then this is a confusion matrix. So it says this is a symmetric, not a symmetric matrix, it's a square matrix there, because we have only like two classes, 0 and 1. And here on the column that shows the performance, the true positive and the true negative in each case. But this doesn't maybe look nice. Maybe you would like to use Seaborn, for example, and utilize the heat map to get a better output. Let me show you how can you get a better output here. I can say, for example, C confusion matrix equal, and I'm gonna again take this part which we already did it before. I'm just renaming, getting another variable and rename it as a variable, confusion matrix, and then I can say SNS heat map. This is a heat map on the C board, and then I'm gonna feed the matrix CM and annotate again as we did before is true, so that we can see the numbers. And I'm gonna use a CMap, another CMap. I'm gonna call it blues. I mean, that might be nicer one. Yeah, maybe. Here we go. So see that I got the confusion matrix in a much better look. See, I have 39 and 65. So these are the correctly how to read this actually is very important. So this means that for the class 0, I have 39 plus 4 different classes. So I have here 41 classes of 0, and I have here 6 plus 65 classes of 1. That's what it means. All right. So that's a meaning, and 39 of the classes were correctly classified as 0, and 4 were misclassified. Here 65 classes were correctly classified as 1, and 6 were missed. All right. If you like to enhance this, I mean, there are many features for the heat map that can improve the performance or the look of this KMap. You can, of course, like here, if you would like to minimize the figure size to make it nicer, you can say fig size. And because if you're gonna take this to an article or a paper or something, and of course you might want to add like X label and Y label. uh, here it has to be fig size equals, okay, 4 and 3. Here we go. So that's smaller. I like this size. I tried different sizes, but I figured out that this size is much better look. Okay. So now I have the confusion matrix. That's great. If in many cases I would like to save this data, so simply I can say plot dot save fig. So this is a saved figure, and I can save this as a confusion underscore matrix dot, you can have it dot bing, for example, something like that. If I executed this, now I can go here. Here we go. I have the confusion matrix. It's if I double click on it, it should appear here. I don't know why it's not appearing. Maybe the size. But if I downloaded this file, if I downloaded the file, and I can download it here, and then I can visualize it. So it should look better than this. Yeah, I think I need also to define some features, which is very important actually when you save the file. I think maybe we need to define the decibel dBi. I would like to say, let's use a resolution of 300, okay, and see how this figure will look like. Alright, so I think that the reason that this drawing is not working is I must save the file here and then show it. Let's see how this works. Now if I click here, confusion matrix, double click, here we go. So that's it. So we need to save the file first, okay, and then use plot dot show, okay. So that will be the best solution for this problem. Now finally, it's the regular procedure that we follow. If we have would like to predict whether the patient has cancer or not, given that if a patient has a mean radius of certain number and mean texture of certain number, then we need to know if the patient has a cancer or not cancer. So the procedure that we always follow is we create a data frame. So I say test patient. I'm gonna test if this patient has cancer or not. I'm gonna create a data frame which has mean radius, and then I'm gonna create list of numbers here. I have what 15.5 comma 12.2, and then comma, and then the other feature which is mean texture. Okay, if you feel like there is some mistakes, you should be able to get it from the check the spelling. That's very important. We have here the values are 31.2, 31.2, and 34.5. And then in this case we can say test, let's call it test patient data frame, control C, control V, and we're gonna call it data frame as we always do. And then we're gonna define dd dot data frame, and then we're gonna feed the test patient, okay. And then we can visualize the test patient here as input. Here we go. Yes, here this is it. Now I want to feed this to the predict model, so I would say prediction equals predict, and then I'm gonna feed the uh, destination data frame, and then shows up prediction. So let's see, the problem predict, this is spelling, there is a problem in the predict. Yeah, I mean, we should write model dot predict, not just predict. Okay, this gave us the output result. Okay, and but of course, if I would like to do it as we do it every time, we can just say add this prediction. So the prediction here is 0 0 0 0, right? Okay, so we can, what we can do is we can add test patient to the test patient here. I can add the column of, I'm gonna add the prediction. Yeah, but I have to call it here first. Okay, let me make sure that it's correct, and then this should equal to prediction. Okay, let's see what's gonna happen. There is still a problem. Let me just copy this. Here we go. So that there was a spelling mistake in the prediction, so it has to be correct. And now if I run this, so that should, so here we go, that's the output. I remember when I did it the time before, there was, this was 0 and 1. I'm not sure if there is any error, but let's see, 15.5, 12, oh, 12.2. Yeah, so here, yes, this is 15.5, 12.2, correct, 13.1, 31.2, and 34.5. That's absolutely correct. Okay, and then when we do the prediction, we fit the test patient data frame. Okay, and then we take this prediction and add this column to the data frame, and then display the data frame. That should give us this output. Maybe maybe I just don't remember the output, but I think that's the output in our case. Okay, you know, when I got an error, if I run this, that's the reason of error. So it doesn't work. Why? Because I'm adding another column, and in reality this only should have only two. That's a problem. So if I run this one more time and then I run this, that gives me the correct output. See that? Because when you add here, you are building the data frame. That's the issue. Okay, I hope this is going to be useful for you. And of course, k-nearest neighbor is one of the very successful techniques. Now, in fact, I want to do something else. I mean, we run all these experiments with k equal 4. Let's see, and the performance was 0.91. Now, what if we run this with another neighborhood? Okay, let's make this 5, for example, or 6, and let's see what's going to happen. If I run this, I would like to actually to check the accuracy in this case. So the accuracy became 0.921, right? It was 0.91. So let me try to get like more neighborhood and see what's going to happen. Oh, it gets bad. So it doesn't mean if you increase the neighborhood, the performance will get better. You need to make a balance between this and this and this. So let me try 6, because the more data, maybe that will cause a problem. So 0.92 is the 6th neighborhood. That looks better in this case. All right, thank you so much, and I appreciate your time.